Which one of these compounds is going to have a higher melting or boiling point? How about these two? Well, in order to understand that, we need to know intermolecular forces. So let's get into that. So what are intermolecular forces? Well, it's basically exactly what it says. It's intermolecular, so it's between molecules, and it's a force of attraction, typically is what we're talking about here. There can be repulsive forces, but for our purposes, we're typically talking about the forces of attraction. So in other words, does Cl2 with another Cl2 have a higher force of attraction? Or do two molecules of I2 have a higher force of attraction? Well, let's figure this all out, okay? So let's talk about the general types of intermolecular forces. We're going to start with the simplest one that everything does, and that's called dispersion forces, sometimes London dispersion forces. And so let's figure out what London dispersion forces are. Well, let's list this off over here as London dispersion forces. And let's start with an example. I'm going to take an atom like helium, okay? So helium is a noble gas. Let's say we have a helium atom, and it has its electron cloud around it, okay? Now, let's say we have another helium atom next to it, and it's over here. Now, let's just say that in some instantaneous moment, the electrons in this helium atom happen to be kind of crowded off to one side, right? Because they exist in a distribution, so there's always a probability of them existing in a certain location at a certain time. And let's just say in one moment, like I said, it just happened to be that the electrons are a bit crowded off to this side for an instant, right? And so what that means is for this instant, this side of the atom is going to have a partial negative charge. And because this side of the atom is deficient in electrons, there's going to be a partial positive charge over here, right? And if you saw my last lesson on polarity, you'll know that that's a lowercase delta. It just stands for partial. So it's not a full-blown negative or partial charge. It's just a partial one, right? And in this case, it's going to be pretty small, right? But the point is, if we have this instantaneous charge separation, well, for that one brief moment, the other atom is going to feel, or the electrons of this other atom are going to feel an attraction to this partial positive. And so what's going to happen is the electrons here want to become attracted, or they're going to become attracted, and they're going to crowd towards the side that the partial positive is on, right? Because positive attracts negative. And so these electrons now are going to kind of do the same thing, and we're going to get this as a partial negative, and this side is a partial positive, and now we have an attraction between the two atoms, albeit it's instantaneous and it's very weak, there is an attraction. That's what we call a London dispersion force, okay? So again, it's this force of attraction between two different atoms. Now, let's say I have another noble gas. So I started off with helium here. It only has 2 electrons. Let's jump down to something like xenon. Its atomic number is 54, so it's much larger. There's a lot more electrons going on, and just it's not to scale, but let's just say xenon is going to look something like this, right? And then we have our other one, and it's, roughly like that. And now let's say the same thing happens. Let's say for an instant, it just happens to be that the electrons are going to have a bit of a higher density on this side than on that side. And so this side of the atom is going to have a stronger partial negative than in the helium, because this is 2 electrons that are a little bit crowded off to one side. Now we have 54 electrons that are going to be partially kind of more dense on one side than the other. So this is a stronger partial negative. And what that's going to do is cause a stronger partial positive over here, and then a larger attraction than in this case to the electrons on the next atom. And so those electrons are going to crowd over. We're going to get over here. We're going to get our partial positive. And so what would you expect to have a stronger interaction? The London dispersion force between 2 helium atoms, or the London dispersion force between 2 xenon atoms? Well, it kind of makes sense that it's going to be the xenon atoms, right? There's more electrons, a larger partial charge, and so a stronger attraction. And, you know, if you just kind of thought about if you took a ping pong ball and you rubbed it on your shirt and you made it static and, you know, you got like a static shock from it, and then you did the same thing with a beach ball, it's going to hold a different amount of charge, right? Well, it's the same idea with the atoms, or we could scale this to molecules. The larger the molecule is, the more surface area it has, the stronger the London dispersion force is going to be, okay? Now, this is the weakest of all intermolecular forces, and every molecule exerts this force. So you just pick a molecule, its electrons can instantaneously kind of be distributed unequally and cause this little partial instantaneous charge separation and have this minor force of attraction to the next molecule over. So everything does London dispersion forces. So now let's talk about the next intermolecular force, and that's going to be dipole-dipole. And this one I guess I'll write out because it's not as many letters. Dipole-dipole is our next one. So now let's go and take a look at a molecule and figure out what's going to be happening with dipole-dipole. And by the way, guys, if these videos help you, please give a like, follow, share this with someone that needs help, save it so you can review it again later. And if you consider patronizing me over here, that helps me to continue making these videos for free. So let's continue. So let's say I have a molecule like, let's do something like HCl. So if we have H bonded to a Cl, we know that by understanding electronegativity, chlorine is a little more electronegative. If you missed that lesson, I have a lesson on electronegativity. It increases up and to the right. Chlorine's over here, hydrogen's there. Chlorine is more electronegative, which means it attracts electrons to itself more strongly. So this is going to be a polar molecule, right? There are lone pairs on here, and we're going to draw our dipole moment. So that means that the chlorine's more partially negative and the hydrogen is partially positive. So we have a permanent dipole here, and dipole meaning this has a polarity. There's a partial positive side, a partial negative side. So now let's just say another HCl is nearby, and let's just draw that over. I'm going to draw it over here at an angle. We have this going on, and of course this HCl it's the same molecule, right? So basically it also has the partial positive, partial negative. Positive and negative are attracted to each other. So we have this attraction between the partial positive of one molecule and the partial negative of the other. So since that's polar and that's polar, we have a dipole-dipole interaction. And because in the dispersion forces, it's this temporary instantaneous dipole that is weak, and that is weak, this having permanent dipoles is going to be a stronger attraction because this is always polar, and so it's always going to feel an attraction to its neighboring molecules. Okay, so dipole-dipole is a stronger interaction. Both of these together are considered van der Waals forces. It's kind of a general term for these types of interactions. And now let's continue on to do hydrogen bonds. So hydrogen bonding is sometimes described as a special case of dipole-dipole interactions with molecules that have an H directly bonded to an N, O, or F. So it's going to be H bonded to N, HO, or HF. But that's not really technically true. And what did I do with my eraser? Here it is. So the hydrogen bonding, although it is stronger than dipole-dipole, it's not exactly the same as just a stronger version of dipole-dipole. There's a little more to it than that. So hydrogen bonding isn't really just a special case of dipole-dipole because it acts at a shorter distance than a dipole-dipole interaction. So it's not just the attraction between a partial positive hydrogen and a partial negative electronegative element from the next molecule over. There's something more to it. So let's take a look at water, for example. And yes, you're bugging. There's nothing different about me than from the last clip. So let's draw out water and take a look at it. And so we have this, right, with this shape. And then let's draw the next water molecule over. And so hydrogen bonding has a kind of partial or semi-covalent character to it. So it is stronger than dipole-dipole interactions in general. And so it's going to be from the hydrogen of one molecule to the electronegative element that has lone pairs of the next molecule over. It has to have a lone pair. And so the two things that are interesting about hydrogen bonds that make it not just a stronger case of dipole-dipole is that there is a directionality involved. And by the way, for most general chemistry courses, you may not be required to know this, but just in case you are, let's understand this. So see how from the oxygen to the hydrogen, we have this directionality? Well, the strongest hydrogen bond is going to occur when you have that same kind of orientation over here. So it's kind of like all in a straight line, okay? And so there is an effect with the orbital that the lone pair is in the electronegative element, and then also with the partially positive hydrogen. We don't have to go crazy in the weeds here, but the point is hydrogen bonding is stronger than dipole-dipole interaction. Although your teacher may call it a special case of dipole-dipole, that's not technically true. It is stronger than dipole-dipole, but it's a different interaction. But again, it's not an intramolecular bond. It's not a true covalent bond. It's an intermolecular bond, okay? Or an intermolecular force of attraction is a better way to phrase it. So we call it hydrogen bond, but it's not truly an actual molecular bond, all right? So that's the last of the major ones, but we're going to have two bonus forces we're going to talk about that you may need to know in general chemistry, and if you go further, you'll definitely have to understand this either way. So before we jump into that, guys, if these videos help, please give a like, follow, share this with someone that also needs the help, save it so you can review it again later, and then please consider supporting me over here and help me to continue making these videos for free. So now let's look at some of these other bonus forces here. And we have dipole-dipole and hydrogen bonding. And I think I meant to leave a little space here. So let's do it like this. Let's put dipole-dipole here. Dipole, we'll just call that dip for now. And then there's going to be something we're going to call dipole-induced dipole, okay? So dipole-dipole is the interaction between two polar molecules. But what if you have a polar molecule and a nonpolar molecule? So let's just say we have dipole induced dipole, right? My abbreviations are getting a little crazy here, but I think you get the idea. Dipole-induced dipole. And so if we have a molecule like, let's just say HCl, and I want to draw it this way for some reason, and we have the electrons going over there, so we have a partially positive hydrogen, a partially negative chlorine, and then let's just say we have a nonpolar molecule, or a just an atom. We can use xenon again because it's easier than drawing a molecule to just draw an atom. So let's say this is our electron cloud over here, and then same with the HCl. We kind of have this tiny electron cloud around the hydrogen, and then the electrons are spending more time around the chlorine here, and so this is partially positive. This partial positive from this polar molecule, this permanent dipole, is going to attract the electrons in the xenon, just like we saw in the London dispersion forces, except this time, now instead of it being that like the first nonpolar molecule just happened to have its electron cloud shift to one side instantaneously, and then you get this little interaction like the London dispersion forces, now we have a permanent dipole inducing a dipole in a nonpolar molecule or atom, just a nonpolar species, right? So the dipole-induced dipole is going to be stronger than a pure London dispersion force in general, but not quite as strong as the dipole-dipole, because if you have two permanent dipoles, now you don't have to induce one, you just have two permanent dipoles that are just always attracted to each other, right? And so this is kind of somewhere in between London dispersion forces and dipole-dipole. And then finally, we'll get to the last one that is typically stronger than hydrogen bonding. And of course, these things all have a range. It depends on the size of the molecules, the strength of the dipole. There's a lot of factors involved, but I'm just giving them a general ranking. Our last one is going to be Ion-dipole. Ion-dipole. It gets sloppier at the bottom of the board here. So let's just say I have, let's just do like water, because water, although it does do hydrogen bonding with itself, with another water molecule, it also does dipole-dipole because water is a polar molecule. And it also does London dispersion forces because everything does London dispersion forces, right? So to kind of remember, as you go on the list, if you can do hydrogen bonding, you also do dipole-dipole because you're going to be polar. And if you can do dipole-dipole, you also do London dispersion forces because every chemical species has London dispersion forces as one of its intermolecular forces, okay? So let's just say we have a sodium ion and let's just say we put salt into water, sodium chloride into water, and the sodium and the chloride are solvated, they're separated. So we have this sodium here and it's positive, right? It's lacking its valence electron, the chloride has it. And now we have waters. Well, let's just say we have our water and of course, whoops, that's not an O, that's an H. The hydrogens are the partially positives and the oxygen is partially negative. It's got its lone pairs over here. So the attraction between the partial negative oxygen and this full-blown positive sodium is going to be very strong, right? This ion is attracting all the partial negatives of the molecules around it. So that's how sodium chloride gets solvated, right? You have a bunch of water molecules and they're all going to kind of line up more or less like this so that the partial negative side of the molecule is going to be facing towards the positive ion. And then if we just kind of reverse this, the partial positives are going to be by the chlorides, right? So, you know, I could have a chloride ion over here, and this is not the scale, but the partial positives of the hydrogens are going to be attracted to the negative charge of the anion, all right? So ion and dipole is stronger than a hydrogen bond in general. Like again, each of these things have ranges of how many kilojoules per mole this interaction is, you know, to break it basically. And so in general, ion dipole is the strongest, then hydrogen bonding, then dipole-dipole, then dipole-induced dipole, and then London dispersion forces. And then when we get to London dispersion forces, the larger the surface area, the stronger the London dispersion force. All right, guys? So in my original question, we had chlorine versus iodine as one of our examples, right? We had Cl2 and we had I2. So which of these is going to have a stronger intermolecular attraction? 2 chlorine molecules or 2 iodines? And iodine is below chlorine on the periodic table. And so that means iodine is a larger atom. And so we have 2 I2s that are going to be larger versus Cl2s, which are going to be smaller. So the London dispersion force, because these are both nonpolar, is going to be stronger in iodine than it is in chlorine, right? This is larger. They're both nonpolar. So if they're both nonpolar, we only have London dispersion. And if it's larger, there's more surface area. And so the London dispersion force is more intense. And then the other example, I think I did methane and was it ammonia? I think I did methane and ammonia. We have, let's say we have CH4 and NH3. They're similar sizes, right? We have a carbon bonded to 4 hydrogens, and ammonia is like this. So methane with methane, this is nonpolar, right? So you do have to be able to tell, is it polar, is it nonpolar? And then after that, you have to figure out what type of intermolecular attractions can it have within its own substance, right? So methane with methane, it's nonpolar. So the only intermolecular force of attraction that nonpolar substances have is London dispersion. So that's it. It has the weakest force available to us, or that, you know, that is exerted as its primary intermolecular force. But now how about NH3? Well, we know it's polar because we can draw out our dipole moments. Whoops. And we know that it's trigonal planar. So this side of the molecule up here is going to be partially negative, And these hydrogens are going to be a little more kind of like they're all sort of down here, right? I'll just move one of them to show. And so this side of the molecule is going to be partially positive. So that means that we can have a dipole-dipole interaction between two ammonia molecules. And so already that is stronger than London dispersion in general. And then also it has an N bonded to an H, and the N has a lone pair. So it's also going to have hydrogen bonding, as it's really the strongest intermolecular force that it has. So it has hydrogen bonding, dipole-dipole, and London dispersion. So this is going to have a stronger intermolecular interactions. And so that's going to raise its boiling point, for instance, okay? So we can attribute physical properties to the intermolecular forces. All right, guys, so again, if these videos help, please support the channel. Check me out over here, and I'll see you guys in the next one.